I'm honored to be here. I'm honored by the many people I've known or have been mentors or people that have helped me or I've known or been pleased to know in the previous years. And especially Professor Rosette, helping me with something so my throat will stay so I can speak. I've known many people, some I've gotten to know just today. I'm quite impressed by the Texas A&M alumni. Sitting next to Darryl Hooper, I can see it when people talk about the alumni and the spirit that's here, and I think it's also terrific to see a kind of a one Texas kind of thing when those people from UT come down here with Roy and Fulvio leading a large group from the UT. Roy Olson, I give credit to a little bit why I'm here today because he was the first professor I met when I was looking at graduate schools. And Roy, I'm still had a couple of good years with Roy at Illinois. And that's probably a bit why I'm here today. So thank you very much. I'm also pleased to see so many students here. And if there's one thing, I'm in a big engineering firm, that we need are new people. We have a new president, and the mission in the next year is to really get hundreds, it's a large firm, needs at least a few hundred new people at entry levels coming into the engineering profession, whether it's civil, structural, highway, transportation planning, mechanical, electrical engineering. There's a tremendous need, and I'm pleased to see many people here. And then I wish to also say that my ex-friend, Tom O'Rourke, for sending that email. Tom and I had some terrific times, did some work on the Washington Metro, and I hate to say it, but most of what he put in that email was true. So I'll speak to anybody who wants to know about that later. I'm going to talk about my experience in project management and evaluation of risk in my career. I'm trying to give you some insights of why underground engineering is, why it's so risky, and a little bit the perspective of why I'm up here today. Why is it risky? Well, obviously there's geology. I'm not going to talk about geology today, but as any kind of construction, there's special construction methods and equipment. There are construction contracts, and then there are those people things. Today at lunch and throughout the discussions today, Clyde Baker talked about the importance of I would say, personal relationships and really communicating well with people. And I think a lot of things go right or go wrong because of the people aspects. So I'm going to talk about these broad topics. Tunneling, it's something from geotechnical engineering. By chance, I got into it. Tunnel contracting practices, what's happened in the last 30 or 40 years, and then a bit of an example on risk management and project management, as at least I'm trying to practice today, and some of the things that I think are important. I also, before I start, I want to acknowledge my co-author, Jim Monsees, who was, we just dovetailed. He was finishing graduate school and starting, but over the last 20, 25 years, Jim and I, who's with Parsons Brinckerhoff, have co-authored things. And the synergism between the two of us, if you ever hear him speak, I think you'll hear him speak about a lot of the same issues and things that I'll be talking about. Well, these are the kinds of things in tunnels that make them interesting. Large tunnels, that was a big one at Yucca Mountain. That built an 8-kilometer long tunnel, 25 feet in diameter, despite nuclear quality assurance. This machine's 11 meters in diameter. It is building a tunnel in the Swiss Alps. A very large tunnel of which Professor Briot had a contribution. This is the Interstate Route H3 tunnel. It's a large highway tunnel through the mountains, and that's where I first got to know Jean-Louis. Came over to do some pressure meter testing back in the old days of the late 1980s. You can see by the size, and if that's it, you can see that guy there is 6'6", so it's a good sized tunnel. There's also large caverns in soil. This is almost an unprecedented thing in San Juan, Puerto Rico. It's actually dug in dirt with about 15 feet of cover underneath historic buildings in not old San Juan, but in the shopping area of San Juan. There's other sequential excavation methods. I'm not going to talk about tunneling methods, but these are the kind of big things, and I'm just emphasizing the size of that person there, that the modern world is going to require these kind of big things to be built. Well, that's the equipment. It's got a whole world of its own. It's like offshore drilling equipment or mining equipment. Everything's got its own special world of expertise, and how well those things are built and constantly improved is an industry and a whole culture of its own. But to make these on the civil works side, tunnel contracting practices have gone through quite an evolution. And consider this statement, if you just bear with me while I read it or read the key words. It says, for several years, it's recognized that the contracting practices in the United States are inadequate. It says that whatever we're doing now in terms of how we procure services, how agencies, states, whatever, that they're not any good. So when was that? Now, I won't ask any of the students because it was way before most of you were born. It certainly was not today, wasn't last year, it was in 1974. So it's a 30-year since that kind of statement was made. It seems maybe benign in perspective of many of the controversial things going on, but there was a crisis in the mid-70s, not just a fuel crisis, not just an oil crisis. And to say that the contracting practices in the United States are inadequate was a comment that occurred because there were major construction projects. The Washington, D.C. Metro had a lot of problems. They were delayed, uncontrolled costs. I can even talk about the Central Artery. I mean, I think it was even bigger problems, more real problems at that time than, say, people might allege on some of the big public works projects today. And fundamentally, from the business side, whether you're a tunnel contractor or engineer, this was bad for business. If you had contracts, nobody could make any money, nobody was happy. Something had to change. So 30 years ago, there was a history of the way things were done from 1974 to a turning point. And then I'm going to talk about some of the developments, some of them which will come into things that the things you do in geotechnical engineering that you might be working on in reports in the coming weeks, months, and years of your career will fit into the kinds of things I'm talking about. How what you do will fit in and have a role in future contracts. Well, prior to 1974, and there's a reason why that date, what was driving the market? At that time, major interstate highways were still actively under construction. San Francisco was just finishing a transit system. Washington, D.C. had started a decades-long process. There were the clean water programs, wastewater tunnels. There was a lot of work going on. I show here the Washington Metro. That's things in San Francisco, clean water. All over the world, there's these major projects. But what was happening? The Eisenhower Tunnel, who has gone skiing in Colorado here, driven out there? You ever drive through that tunnel up through the mountains? Anybody ever remember going over Loveland Pass? Scare you to death, you know? Well, those tunnels were hard fought. The first one, there's a whole story. That tunnel on its own, that's the right one when you're going west, changed the paradigm of what it took to build these big projects. A lot of things happened because that job came to a dead halt, hit a huge fault zone in the middle of the mountain. Water Tunnel number 3 in New York was also legendary and also a problem. Clearly, there was something new needed, innovation, new ideas, better ways. We were really living in the 70s on the practices that had gone on, in my view, although I didn't know them personally, a lot of the World War II, post-World War kind of ways, the old-fashioned ways. It was therefore an opportunity for change. Tunneling methods were changing. I'll just talk to them. I've given this talk to people who are tunneling. Different methods. The U.S. was frankly old-fashioned. Europeans were coming in, changes in tunneling methods, and eventually pressurized face tunnel boring machines, very special things that had to be sort of sent to them in the 60s and to Japan and then came back in spades to us today. Ground reinforcement. I'm thinking of a time when if someone said you would use a geotextile and use it to reinforce a pavement or something like that, they'd think you were crazy. Those things were unheard of in the 1970s. Maybe not everywhere, but there have been so many changes of things we put in the ground we used to throw away that they are now permanent. Well, certainly things needed to change. 74 is a turning point, and this is the document, and I put it up here as a copy of it because I'm probably going to disconnect completely because it says here, I could point otherwise, that's like typewritten. It's a National Academy but it's actually of that era, probably wasn't a typewriter, but it has a look. And this one document made a lot of recommendations. It was a consensus document greatly to recommend 17 things. I'm not going to go through it was, but it had the contractors and engineers and leaders in the world. It was the best of the day. It was powered with the U.S. National Academy sponsorship, and it was really just in time. But it had several things that maybe we take for for granted today. First is disclosure. In contracts, I'm speaking about these big tunnels, but it would be a foundation engineering contract, it would be any kind of civil works project. Disclose all subsurface information. Like if you did some borings, you didn't like what they looked like, so maybe you just put them in the drawer and you got another set of borings. That's called cheating. Well, you can't do that. That was bad. That was bad. I mean, people would do, or they'd say, I have borings. I don't know if it's right or wrong. Disclaimers, don't make them. And change conditions, acknowledge those. Finally, federal practices got the change condition clause. And I'm sure, and I'm asking the geotechnical consultants here, do these all sound familiar as regular practices now in practice? They used to not be. There were things were bad, and when they went from, let's say, projects on highways, bridges, went to these major, huge, heavy underground works where billions of dollars were spent over the years, the problems became huge. Something needed to change. But the theme now that gets me to risk, that really all of these things, we're dealing with risk, trying to manage it. And since that time, there have been landmark developments. There's been sort of 3 cycles in 89, 97, and 90. I will show them. I don't know how many people have ever seen these books, but in 1989, these books came out, and they're called Avoiding and Resolving Disputes in Underground Construction. It's like how to not have a problem like that. A couple cycles of those. And those were helpful because it codified things, but note that it took 15 years from 1974 to 89, if I have my math right. In 1989, what came out, and I was a part of this, part of that first gray book, it said, hey, those things in 74 are pretty good. It got formalized with industry consensus. It came up with things with geotechnical data reports, a geotechnical design summary report, and some other things. Let me just talk about a geotechnical data report. I keep looking at these Texas students down here. I guess I could find some UT students to pick on in a minute. They're back there that I know. Maybe none of you have been in practice, but often you write a report, you go out and drill holes. Have any of you ever done that? Write a report, borings, lab tests. Somebody please say yes. Yes. And you get a lot of data. In a classic way of working in consulting, the facts were here, and then here's my recommendation. And on something that goes on a long way, so those recommendations will conflict as a project evolves, especially if it goes over many years. There was great confusion. So something evolved where you had a data report, a GDR. It separates facts from interpretation. It's intended to be contractual. Something else called a design summary report, and for these very specific things, dealing with the risk and tunneling, it placed that prior work in perspective. It would say, we thought about this, but then we decided not to do that. It would clear the air on what the old work would do. It also brought in the construction methods to design. It said, it's not like here's theory, now you contractor go out and build it. It's really trying to relate the practical stuff, that the design was constructible. It presents the interpretations, and more importantly, it was starting to require the engineers to understand and improve designs. Because when they had to write down, why'd you do that? Most of them had a hard time. Well, these are the recommendations and guidelines over the years, but there's a few problems with this design summary report. One of them was the tunnel contractor, or I could say a foundation contractor. That person, that entity had a wide range of thoughts about what they thought the geologic conditions were. And those old reports, the styles, they really didn't have any teeth. They were kind of here, they're nice information. Limited construction status, helpful but did not really solve the real problems on risk. Gets us to 97, geotechnical baseline reports. And who's ever seen this little yellow book? Is there anybody other than Fulvio? Yeah, gosh. This is not arcane. It's published by the American Society of Civil Engineers. It's a decade old. I do think now, since this is quite a geotechnical audience, that the baseline concepts for foundation contracts could be there. I haven't talked to Clyde about this, but I think those things could be there to manage risk on difficult jobs. What does a geotechnical baseline do? Well, it helped define and make people really understand the geology and the tunneling method, that they were linked. It wasn't just providing information. It was really a major advance in contracting practices. And it's widely, maybe not widely, but it's generally accepted for tunnel contracts because it will establish, it says, and I'll give you an example. I think I've got an example. There's a certain art to it. It has to be relevant. And I want to get to an example of what's a geotechnical baseline. Now, tell me, is the permeability of this ground and this will apply to digging a hole, ranges from 10 to the minus 2 to 10 to the minus 5 centimeters per second. And if you think in millimeters or meters, please convert, or inches. Would that be something you could tell a contractor that he could base a bid on to, say, dig a hole in the ground? That's 3 orders of magnitude? Probably not. How about boulders will sometimes be in the tunnel horizon? Sometimes. There's a weasel word. There's a geotechnical word. But how about crystalline bedrock will not be present? Yes. I got a tunnel in dirt, soil, and I'm not expecting to hit those right out. That would be a baseline, and a contractor would not have to put money in that. I think this principle is very applicable to anything underground, not just tunnels. Well, the baselines have had problems. People started. They didn't have enough contractual importance, and the reports are too darn long. They're starting to get to be works of art in themselves. And it was not dealing with the fundamental problem of the risk and whose risk is it. So that gets us to kind of my little bitty summary here about risk management and risk, that over the decades we see if there's a hazard. The old reports, we did this. We didn't really quantify what the risk was. The design is supposed to mitigate and eliminate things, but it's not a very structured process. And then we like to allocate the risk. Mr. Contractor, you do this, I do that. Usually owners want to give all the risk to the contractor. It was being imperfectly done. These geotechnical bases should be risk allocation. But globally, I think you'll hear risk everywhere. Talked about. There is a groundswell of things. These reports are the International Tunneling Insurance Group, the International Tunneling Association, the UK Code of Practice. They're all dealing with the same things. And the things I want to tell you about today, that there's 2 major things going on. And the third one is what I'm talking about. There is an update of the 74 guidelines. It should be out in 2007. This is the leaders, Bill Edgerton, who's the president of Jacobs Associates. Jim Monsees is on that committee. And it's working on those recommendations and really looking at where are we to try to get industry consensus on several contracting provisions. I can give you details. Several of them are in the paper. The other one is updated geotechnical baseline. Randy Essex, who's now with Hatchmont McDonald, a long time with Woodward Clyde, has been pushing that. And that's updating, which would be the yellow book. Where has project management and all this mess and all these good and bad things have happened? And I think this is a little harsh, not always the way. A designer designs, a contractor constructs, and you don't mix the two. That's not a good way to work. Once again, I give credit to Clyde talking with the students of how, you really need somebody out there. You need to keep in touch, and how bad it is, unless on any difficult job, that you have to have people out there to see whether the design things are really like what you expected. So the management of design, which is what I do, is still having problem projects. And we have these terrific good risk management tools like the baseline and data report and sorting all this out. But often these things are just not in time. They're not complete, not coordinated. That's a big thing, different people, and sometimes not enough. And this is the line that I'm pushing, and Jim and I are pushing, is you really need to have this thought of risk management, not as a buzzword, not as a popular thing like, I'm trying to think of another buzzword, embedded in the project management process. I'll give you an example toward the end. I show here a typical curve where if you have any project where you have risk, whether it's geotechnical or let's say even more risky to most people, is renovating a bathroom at home. All right, the best place to save yourself money is before you ever get started in construction. Do your preliminary design and you straighten out with your spouse, yes, I want the toilet here and the tub there, and not the other way around about halfway through. So you can reduce the risk, as I've shown, substantially during preliminary and final design. When you're out in construction, something that's not dealt with is difficult to deal with. So the risk management process, I will not go through the rigorous part. You really have to identify things as hazards, and it's like this. You identify, quantify what it is, then you want to get rid of it, mitigate it, and allocate it. So I'm going to give an example here in a minute about what a hazard is. A hazard is an event having a consequence. And a risk is like it's going to happen often or not so often. So hazard, let's say, is something bad. I'm going to give this example, and I'm going to quantify it like this. It's a chart like this, 3 by 3. And this is a risk, and I'll give an example in just a minute, that has medium probability but high severity. Now let me just, then the whole process is, if you're into charts and so forth, which can be, need to work to not have that become your life, is that things that are rated the highest risk you've got to get rid of early. There'll be eventually some risk to a project that you have to deal with during design, and whatever's left over, residual, gets allocated somewhere. Somebody, the owner says, I'll take that risk, the contractor takes it. So now, here's an example. Texas A&M football team not winning Big 12 championship. Is that a hazard? I don't want to see you guys down here, but. So I want to quantify that, and I'll tell you why I'm bringing this up. So the impact of A&M not winning, is that a high impact? It'd be turned around if I give this talk at Austin, but probability of A&M winning. Now, there's a different version. There's probably a version of that in September, and a September to November. So on the chart, it looks like this. So in September, impact of not winning is bad, but it's low, new season. November, oh yeah, I think where you're at. Now, if you guys didn't hear, I wasn't here 2 Saturdays ago, last Saturday, because I am a Cornhusker graduate of the University of Nebraska, and I think they played football down here last Saturday. And I thought maybe I'd tell you that only when I was on the way out of the door. I don't think you're in the contention, but obviously have a huge stadium and a great football program. The mitigation actions, though, to get the example, what would you do if you're having a losing season? You'd want to avoid that. You'd want to take that action. And you typically, the thing you should do, recruiting, new coach, you fire the coach, new stadium, or expensive box seats. Those are the usual answers. I haven't heard that you're going to get a new coach, I don't think. But that's the usual thing. You kind of find somebody to blame and move on. Well, the big picture. For each hazard, whether it's football, and you can apply this, you need to identify it, figure out how bad it is to you. It's very local to your project, and then allocate everything for every risk. Now, I'm going to give you an example of a project that I'm currently working on, and I had a great progression. I went to Hawaii, went to Las Vegas, went to San Francisco, and it's that plot of something desirable, and then Detroit. And I guess I didn't do too well there, and I'm actually quite pleased. I feel I have a good business reason, certainly have a good business reason to be in Detroit. This is a tunnel. It's an animation, which I didn't make, of a tunnel. We'll maybe play it the second time. That's being built as an outfall tunnel going out to the Detroit River. A tunnel's been built. That's the red one. I'll show it one more time. That is failed. It flooded 3 years ago. The new one is blue, and we have to design and construct a new one. It's about 300 feet below the ground surface. There's also an existing tunnel. I can show this. I'm maybe not going to show it again, but I'll show other pictures of it. It's a fairly risky project. I didn't move there explicitly to do this job, but again, it's a project that has an existing tunnel. They sunk 100 meters down a shaft to get an outfall tunnel. This is the Detroit River. Canada's this way. Typical oil field kind of operation of huge diffuser pipes out in the river, a costly venture, a lot of money. Flooded the tunnel, it's a new design. And I started on the design of that about 3 weeks ago. So I'm just going to give you a few of the things of what we're doing on this project to illustrate project management and risk management. This is the project I just showed you. This is just some terrible areas of the world. Anyone who has, this is the Detroit River, Canada's that way. One of the world's largest wastewater treatment plants over here, nearly 2 billion gallons a day come out this thing, and they need a second pipe to get it out here once it's treated. And they can't meet a lot of environmental permits. If anybody knows the movie RoboCop, that movie is filmed out here in some old steelworks. Well, here's the project. It's 100 feet deep. It's got soil and rock, Detroit River. This is the flooded tunnel. A very good tunnel contractor. Things didn't go right. I know a lot I won't even say. But there are 6 10-foot diameter, inch-and-a-quarter thick steel pipes out there to bring this waste, the treated effluent, out in the river, just sitting out there, waiting to be used. We have to build the new tunnel. It has a lot of hazards, 200 feet. Even when it's raised up, that's 6 bar, or about 600 kilopascals. High water pressure, hydrogen sulfide gas, and methane. We have to deal with just the tunneling itself, the hydraulics. There's very little head. And I'm going to click through this, if I make it here. Just the sequence, if everybody understands, you're looking at a profile, existing shaft that's 300 feet down, about 30 feet in diameter, and it's in soil over sedimentary rocks, limestone, and some other things. The tunnel's been abandoned. It's full of water. In fact, it's even got artesian water. We were out there the other day. It's got a collar around it. It's got 10 feet of water extra, coming from the rocks up somewhere up toward Ypsilanti or somewhere, a place like that. We're going to grout around the machine, concrete up the old tunnel, put a plug in the shaft, concrete the whole thing up, do a bunch of grouting, create a shaft, build a machine, one of these big machines, a tunnel boring machine like I talked, and a starter tunnel, build lining, get that, it'll be a closed face machine, and then proceed tunneling successively out until we get out to the outfalls. We have to connect to these existing access shafts. And so out in these 6 pipes where the effluent comes back up, you have to hook them. This is what they look like, and the way the arrangement is, the one's right in the way there, so we have to take everything apart out there at your 200 feet below the Detroit River and the shipping. This is what it looks like underground, will look like. There's a tunnel that under pretty tough conditions, you got to go out and dig a big hole, like that big, 80 square feet, or something maybe as much as 100 square feet, to get the effluent out into this pipe safely with a bunch of temporary things to eventually get yourself a connection that is smooth and hydraulically efficient to diffuse this effluent out in the river. And the river's moving right along. It's not like dead water. It's moving at 5 feet per second. It's a connector. It's really a strait between two Great Lakes. It's not a true river. And then complete the connection. But the risk management process facilitates decision making, and these are the things that we do. In this process here, it's colorful: identify hazards, quantify, and a 9 over here is the greatest, such as excessive groundwater is a major risk. I think you got a lot of groundwater anywhere, that's a big problem. It's a hazard, it's a risk on almost any job. And so that would rate a 9. And you want to do something to get it down to a manageable risk. That will require these special machines. Exploration also requires certain contracting practices. Probably the most difficult things will be to work with the city of Detroit on a contract that might be fair to do this work. So this is called DRO2. Risk management in this project links these things because there's so many things. You can't just do this design, that design. There's a lot of things that have to fit together. And so we're dealing with tunneling and hydraulics, and this is the process. And as I show month 1, that was actually October 31, the long delayed project. And we will have a series of risk management workshops. We'll go through those things, identify them, quantify them. We'll get the state regulators to sign off on them, and then we'll mitigate and work on the fundamentals of getting these things allocated to complete the final design and get this thing out in a contractor going on this job in 2008. Well, I've talked tunneling, I've talked tunnel contracting practices and what I've seen in the last 30-some years. And then my own particular spin of where we're going in our company and what I do, risk management and project management, the two need to be together. And the major conclusions that the contracting practices are not static today. Best practices being updated, and I think the trend is to integrate so-called risk management in a very practical way, not a theoretical way, to actually manage and get projects constructed. Questions? Thank you very much.
We seem to be doing relatively well in calculating the risk and evaluating the risk, but on the other side there's a target risk. Do you have a difficult time in establishing what is an acceptable risk?
I want to comment on 2 parts of that. One is knowing and quantifying the risk, and then it's actually doing something about it. We're often good at, we don't do anything. We too hard or can't be done. The other part is quantifying. What I didn't talk about was the calibration of things. we found that on many things, you have to calibrate the sensitivity to that client. And I didn't show them like the details, like if it was some issue in construction, this project, but another one for this client, which is the Detroit Water and Sewage Department. If something costs less than $500,000 on construction, that was not a problem. It was a $500 million job. Now, other jobs, $500,000, oh, that'd be a big deal. It might be $50,000. There was a cost issue. There's also a lot of public relations issues. And it came down to how many phone calls to the mayor. You know, one call you might be okay. The second call, you're dead. That was high impact. So I don't think, I don't know that I completely answered your question, but there is a big activity to characterize what people really, what their perception, their reality of what's an impact, what's a loss, what's a risk. And that's where you got to work with your owner. That's why the owner has to be there with you. Fulvio's going to ask his questions later.
At what level of the company does the decision of the acceptable risk take place? Do you think that should be an engineer's decision or manager's decision? Or?
Well, risk is of all sorts of things. There's risk, there's business risk, and in the management of our project, we have a risk management activity that is very private to the company, that as the project manager, and this in my turnaround, the senior people, we deal with our risk. It's really contact, risk, cost, liability, and we deal with that. But that's not something that winds up in the design. That's how we do our business, and we've got to take certain actions. And that really gets high level. There's only, say, one person between me and the company president. Other work on the project is a different aspect. That's really clients and projects, and that's a more distributed thing that often takes really the owner, and that's hard to get those right people there too. It takes really the director of the department or the chief engineer sometimes to really weigh in, and that takes a lot of effort.
Yeah, how much money was left in the ground when they abandoned that one tunnel plus the tunnel boring machine, and had that risk been allocated before that happened?
Well, the contractor had insurance for the machine. I think they got paid for loss of the machine. I guess just because I don't want to say tens of millions, it's about a $100 million project. But so they're going to wind up paying about 1.5, 1 3/4 times what they should have, and they're about 10 or 15 years late getting it done. Environmentally, it's a decade or more late. So it's a lot of money. I don't think so. It was a design that was done, I think, with some best intentions that went really bad. And they got unlucky. And the technical detail that was very insidious is and I'll talk a little geology, geotechnical, there's limestones, there is some karst around there, but there were some anhydrite layers that I think are very soluble. And they found that they were grouting to control the water, but when they didn't, they just tried to pump more, and they found when they really looked at the numbers, the permeability was increasing. They were washing out something. Something was changing. This anhydrite was going, whatever it was the joints were getting wider, and the water, the effective permeability of the rock, or transmissibility, whatever it is, it's getting worse. It was a no-win deal. And they weren't going to get there with just more pumping. And so it became and they finally got so much they were able to leave the tunnel, but they basically became abandoned. And it's a loss.
How do the U.S. tunneling practices compare with those of, say, in Europe and, say, South Korea, for example, in terms of managing risk? Are we managing risk in the U.S. similarly to Europe, for example?
Well, I think a lot of it is how it's managed in the contract. I think everybody who's got equipment and so forth. I think in Korea, from what I've seen, they are very good at doing things. They're not doing that much by machines, and they have a lot of people with their hands on that, from what I saw in Seoul last year, or earlier this year, that their risk is managed by having people out there that know it. They're miners, and they see something going wrong, they take care of it. And that's why they're successful. They mine large tunnels. They don't necessarily use these big machines. They'll get there eventually. So their risk is managed by having the people out there. The people know what they're doing. In Europe, it's a different situation. The contracts are a bit different. Some of I don't know whether they do any better. The whole global insurance business is worried about this. It's an international tunnel insurance group so it's a problem. In some projects now, the insurers are telling you what you can build, which is not good.
If you had one piece of advice to give to the students that are here, what would it be?
Construction experience. I don't care. You can be the best designer in the world. You just got to go out there and see what it is. If you haven't seen it, I have worked with different companies. I don't know, everybody must know Kiewit, or is it Gilbert here in Kiewit? Frontier Kemper Trailer, the Shea. And you really can't work with those folks until you know and understand their business. You just aren't, and that takes some time, unless you just don't want to be involved in that in different aspects of it. But that's what's made the difference in my career. I worked a summer for the Kiewit Construction Company. And I think I decided after that to go into geotechnical engineering, actually. No, it was a year later, actually. But I worked, I'll just tell you where I worked. I worked 3 summers. I worked for Denver Public Service. Found out nobody knew anything about transmission power foundations. I still stunned today. And worked on the first, was a pump storage project. Worked for Kiewit Construction Company on Lock and Dam. And I worked a summer for a geotechnical firm. I wound up going to school in geotechnical engineering, but I learned a lot. I go back to those things, and I found when I had a job with Kiewit as my client later years, that some of those same people, we could talk about them from 20 years before. I learned a lot. I think that's good for anybody that's involved in civil engineering.
It's a certificate of appreciation to thank Dr. William Hansmeyer for delivering a special lecture entitled Evaluation of Risk Management as a Project Management Tool in Underground Engineering. Thank you very much.
Thank you very much. Privilege.
Now it's my pleasure to introduce the Buchanan lecturer. Mr. Baker received his bachelor's and master's degrees in civil engineering from the Massachusetts Institute of Technology and joined the staff of STS Consultants in the fall of 1954. Over the past 50 years, he served as a geotechnical engineer for many high-rise built in Chicago. He has also served as geotechnical engineer consultant on 7 of the 16 tallest buildings in the world, including the 3 tallest in Chicago and the 2 tallest current buildings in the world, the Petronas Towers in Kuala Lumpur, Malaysia, and 101 Financial Center in Taipei, Taiwan. Mr. Baker has shared his knowledge and experience with his peers through numerous conference and universities lectures, technical articles, papers, and publications. He is the recipient of the Deep Foundation Institute Distinguished Service Award, the ASCE Outstanding Service Award, the ASCE's Thomas A. Middlebrooks and Martin S. Kapp Awards, and 3 meritorious publication awards from SEAOI, including the History of Chicago Building Foundations, 1948 to 1998. Mr. Baker has been very active professionally on both the local and national scene. He has served as chair of the Geotechnical Engineering Division of ASCE before it became the Geo-Institute, as editor of the Geotechnical Engineering Journal, as chair of ACI Committee 336 on footings, mats, and drill piers. He is a member of the National Academy of Engineering and was the recipient of the ASCE Ralph B. Peck Award for the year 2000. Mr. Baker is past chairman of STS Consultants, a 550-person consulting engineering firm headquartered in Vernon Hills, Illinois, and currently serves as senior principal engineer and senior vice president. On about 3 days ago, Clyde sent me a paper that I thought was really interesting. The title is called Risks and Rewards, a Career Retrospective. And I want to read to you, it's kind of a David Letterman top 10 list of how to succeed in geotechnical engineering at a broader scale. So he's got a list, and I'm going to go through this. 1, association with good people. 2, openness to opportunities presented. He adds, problems are always opportunities. Desire to learn. Strong work ethic, being committed and accepting responsibility. To have or develop good communication skills. To share the credit, with all involved, to encourage and involve young staff, to concentrate on problem solving and not on assigning blame, to have an honest and direct approach to fair and equitable solutions to technical and non-technical issues, to have a genuine interest for people and for caring for people, building relationships, to get involved professionally and socially, and to have a positive attitude to enjoy what you do. He then adds that of all that list, the two that are most important in his mind are the first one and the last one, association with good people and have a positive attitude. His talk today is entitled In-Situ Testing, Soil Structure Interaction, and Cost-Effective Foundation Design. Please welcome the 14th Buchanan lecturer, Mr. Clyde Baker.
Thank you very much, Jean-Louis, for that introduction. Excuse my voice, I have a slight cold. It's a great honor and a privilege to be here, to be the 14th Spencer J. Buchanan lecturer, and to share what experiences that I've had over the years. That list of 10 or 12 or whatever that Jean-Louis read, I don't pretend to score 10 on all of those, but I did feel that they were important. My talk today is on in-situ testing, soil structure interaction, and cost-effective foundation design. The objective, to show how, in my experience, the pressure meter has been helpful in better predicting how the ground responds to building loads, particularly in pre-consolidated soils, and how, with cooperative structural engineer and geotechnical engineer interaction, this can facilitate cost-effective and innovative foundation design. In Chicago, we're lucky. We have a lot of pre-consolidated soils, and we have a good community with between the geotech and the structural engineers. Historically, structural engineers have been reluctant to mix foundation types or foundation levels on the same structure for fear of potential differential settlement and their lack of confidence in settlement predictions. Early in my career, when I arrived in Chicago, there weren't too many geotechnical engineers around, and these old-time structural engineers, they didn't see any reason to listen to some young kid out of MIT. But over the years, the structural engineers have developed greater confidence in their geotechnical brethren, and we do operate in an integrated way now a lot of the times. The Chicago history. Our company was, I believe, one of the first companies to use the Menard pressure meter as an in-situ testing tool. It was developed by Louis Menard when he was at the University of Illinois, and we started using it in the Chicago area in 1969. We found that following the Menard empirical rules for using and interpreting the data obtained from the test, we were able to do a good job of predicting what was going to happen when a building actually loaded the ground. And we had case histories to confirm this. So we developed our confidence in the use of the pressure meter in our geology. I just want to show you a typical soil profile in Chicago with the different foundation elements. We have usually fill or sand at the surface. It can vary from a few feet to maybe 20 feet. And then we usually have a stiff clay crust, fairly thin, and then a fairly extensive soft to medium clay, underlain by gradually stiffer clays, and then down to a hard pan, a very dense mixture of clay, silt, sand, and gravel, sometimes overlain by a water-bearing silt and sand layer. And that hard pan can sometimes have a plastic clay layer at the bottom, and then underlain by saturated silt, sand, gravel, and boulders, fractured rock, and then sound dolomite. And you can see listed on here the different foundation types. Footings and mats up in the stiff clay. In the early Chicago history, The building, all the tall buildings up to 20 stories or so were supported up here, and over time they settled excessive amounts. I think the auditorium building has settled differentially, like 18 inches, and maximum settlements are well over 2 feet. And then different caisson, belt caisson levels, and different possibilities here. And then, of course, low capacity piles that stop above the hard pan, and high capacity piles that go down to rock. And this is a little history of the allowable bearing pressures on Chicago hard pan. Pre-World War II, the allowable bearing pressure was 6 tons per square foot. By 1955, with soil mechanics had developed a little bit, and they were bravely increased the bearing pressure from 6 to 7.5 tons per square foot using a formula 1.2 times the unconfined strength. That was increased later to 1.5 times the unconfined strength. And about 1965, the highest bearing pressure had been up to about 15 tons per square foot. And this was by using triaxial compression testing to take advantage of some of the confining effects for the Chicago hard pan. And then 1969 started using the pressure meter, and by 1980 with bearing pressures were up to 20 tons per square foot. By 1987 up to 25 tons per square foot. And the highest bearing pressure that has been used on hard pan in Chicago was on a local basis of 30 tons per square foot. However, the city of Chicago has stopped us at 25 tons per square foot, no matter what our testing shows. We took small steps, as you can see. The determination of pre-consolidation pressure. We found that that's very important. The early research by Lucas and Debussy indicated the pressure meter creep pressure was a good indicator of the pre-consolidation pressure. And the nice thing is that the pressure meter test is a much quicker test. If you try to determine the pre-consolidation pressure with consolidation testing, you've got to have good undisturbed samples, and you've got to have the time to run the test. This is just showing typical pressure meter, or I won't say typical, an illustrative pressure meter curve, the way we run the pressure meter test. We run a unload reload cycle, just around the creep pressure. We unload and then reload again and go up towards the limit pressure. We like to have this this unload reload cycle. Lots of places in the world they don't run the unload reload cycle, but we like to use it. And the rules that we follow with the pressure meter, we have local rules that have that make sense to us and have worked over the years. And that is that the dead load pressure plus the long-term real live load pressure plus the effective overburden pressure must be less than the creep pressure. And the reason for this is just so that we can rely on the settlement methods that we use, where you're sort of assuming a pseudoelastic relationship. The allowable bearing pressure. In the early days with the pressure meter in our consolidated soils and with the granularity of some of them, the way we calculated the bearing pressure in those days using the Menard rules, the bearing capacity was never a question. And that's because the K value was fairly high. Over the years, investigators have found that the K value is too high, and that K value has been lowered, and now it's typically in the range of about 0.8 to 1.4. We have 1.8 here, but seldom use higher than 1.4, depending on the depth to diameter ratio and the material type. And that, so with these lower K values, the bearing capacity has to be checked even on our Chicago our Chicago hardpan. A settlement theory is using the pressure meter data. Well, the two most common procedures that we use are the semi-empirical Menard procedures. And for those of you who are familiar with the Menard procedures, this is the formula. I won't go through it now, but it's in the paper. And it's also, all of this is very extensively covered in Professor Barrette's book on the pressure meter, which I strongly recommend anybody who's interested in the pressure meter having that book in their library and using it. I just go through quickly the old Menard rules that we still use, the layer system that he developed, and his, as I understand it, this is in the early days he correlated it with his experience, and so that's why it's semi-empirical, and it works very well in our consolidated soils. And the Menard alpha factors, we still use the Menard alpha factors. We modify them slightly. We take as an alpha factor the initial reload modulus divided by the initial modulus divided by the reload modulus as a starting point on the alpha factor, but we don't go below typically the values that are given by Menard, except that we do use an alpha factor of 0.5 on our hardpan, and we don't go below 0.3 on the granular soils. And the other procedure that we use for predicting settlements is elastic theory approach, where we use the pressure meter to give us a first crack at an elastic modulus, and we use the formula indicated here, which is Christian, and I forget the author's name at the moment, but it's a common formula for using elastic theory for the settlement prediction. The U factors, there's this one, the U1 and U2 here. I think I've got the right numbers. Christian Carrier, yeah, it's in their paper, and we find it very helpful using these formulas for predicting the settlement with the pressure meter modulus. And the only question is, what modulus do you use? And in the case histories that follow, you'll see what we've done. We try to correlate with building performance. And early in Chicago, or about 1975, the tallest reinforced concrete building in the world was the water tower place. And we use them, it's supported on belled caissons in the Chicago hardpan, and we use the pressure meter to predict the settlement of the building. And the settlement prediction was 2 inches, which was rather significant, and the Chicago Building Department doesn't like to accept predicted settlements over an inch, but the predicted settlement here was 2 inches, and back in those days, we were able to get it through. We actually have more trouble now getting anything over an inch through the Chicago Building Department. The measured settlement after construction was ranged from about 1.7 to 2.2 inches, with an average measured settlement of 1.94 inches. That's remarkably close to the predicted performance. With such a heavy structure like that, that gave us a lot of confidence in being able to use the Menard rules that we've been using in our pre-consolidated soils in predicting settlement. And once you develop some confidence in being able to predict settlement under load, it does open up possibilities for what you can do sometimes in saving money on foundations. And you'll see a number of case histories here to illustrate that. However, to further confirm our confidence, or to further improve our confidence in the prediction methods that we were using. We took the caisson load tests that we had. There were very few of them on the Chicago hard pan in those days. Very expensive to run big load tests. But we took the few that were available, took the soil information from that area. If it was an old test like the Esposito test at Union Station, that was done about 1919, I think. No pressure meter data available then, but we had boring data in the area with pressure meter tests, so we would use that data and predict the settlements, and we would predict the settlement at the point that we would use, for the building load. But then we would go back and correlate it with the caisson load test data at the half point, factor of safety of 2 point, and see how it compared. And we got very good comparisons, at least good enough that we were able to substantiate our confidence in using the pressure meter for predicting settlement. First case history I want to talk about is the AT&T building in Chicago. By the way, all these case histories that I'm going to talk about are written up in papers, so that if you want to go into further detail on the papers, on any of the information, it's all available in the papers, and the reference list is at the end of the paper. The AT&T building is about a 65-story building in Chicago. It was built on a site that already had a former building on it supported on caissons. There was a parking garage. It was built, and the caissons were in the way. Caissons were in this, existing caissons were in this sandy clay hard pan over the whole center portion of the site. So the initial design, because of the presence of all those caissons, the initial design was to put the building on rock caissons. And the developer said, this is much, much too expensive. Isn't there any way we can use belled caissons on this job? In Chicago, the typical ratio of cost between rock caissons and belled caissons is 3-to-1. So if it has to go on rock, it typically is costing 3 times as much as if it could go on hardpan. So the only way it could go on hardpan is if you could construct the center core caissons through the hardpan down in a very dense water-bearing silt, underlain by hard clay and very dense gravel down to the limestone bedrock here. Here we go, limestone bedrock here. The problem with that, of course, is how do you prevent blow-up in this very dense silt, sand, and gravel? If you're going to try and construct a bell here, and the head pressure down here was up about, I think, I don't know if it shows on here, but there's a pretty high head. And at the time that this was going on, that head pressure from the rock below had actually been pulled down in Chicago quite a bit by the deep rock tunnel system that was being built in Chicago. But even so, at that point, at the time this was being built, I think it was about 1986, the head level was maybe up about -50, and here we're down about -70 something. So there's a 20-foot head level in this material. So in order to get this completed, we had to install a filter dewatering wells down to this permeable gravel down here, down to the fractured rock, and pull the water table down to below the surface of this dense silt so that we could construct these bells. And this was successfully done, but the perimeter caissons could be supported up on the hard pan. So we had perimeter caissons on the hard pan. We had the core caissons down on this very dense silt, and we had pressure meter tests in the hard pan and the very dense silt in order to see if the differential settlement was going to be acceptable. And I won't take the time to go through the calculations are in the paper also. I won't take the time to go through the calculations, but we use the procedures, the Menard procedures for determining the effective modulus and then calculating the settlement. And the calculated settlement at the end of I think this wasn't at the end of construction. I think it was about, with construction, maybe 70 to 80% complete. Calculated settlement for the full load was 0.6 inches. At 80% load, the calculated predicted settlement is 0.48 inches. That was for a 12.5 foot bell, and for a 17-foot bell, 0.72 inches. And then by elastic theory, we did the calculation and the settlement prediction using the elastic theory, using the modulus determined from the pressure meter. And I should mention that for Young's for the elastic modulus, we typically use the reload modulus from the pressure meter test, and not for any theoretically justifiable reason, but because it seems to work or we're trying to find some correlation that works in our geology. And what we found is that what actually works, we tried it both with the rebound modulus and with the unload modulus. And what we find is that the highest modulus that we can get out of the pressure meter test is the modulus that seems to work best for us in predicting what's going to happen settlement-wise. For instance, here, when we use the rebound modulus is quite a bit higher than the reload modulus, and then the predicted settlement is 0.43 inches. And this is at 70% load. The actual settlement was pretty close to the settlement. The building was monitored, and the reason we doing the calculations at 70 to 80% load on here is that's when the settlement data was available, and the actual measured settlements were right in line with the calculated settlements. So that gave us quite a bit of confidence. Now to another very interesting case history. This is a Southside office building, and it was had a soil profile. On the south side of Chicago, we have a sand over thick deposit of soft clay, and the clay is typically even softer than it is in the downtown area, and underlain by stiff clay, but the hard pan was missing. And so that the original geotechnical engineer had recommended supporting this 12-story building on, again, either rock caissons or driven piles. And the developer said it's going to cost too much. So the developer asked, isn't there some other way that we can reduce the costs? Isn't there some way that we can build over this the profile without going to rock? And so the concept that was developed and applied was to use the sand layer as kind of a mat, and put either a mat or strip footings up on the sand layer, knowing that you're going to get a lot of, if you just did that, you'd get excessive a settlement in the soft clay. Bearing capacity wise, it just barely works with a factor of safety of 2, but you get excessive settlement because of the soft clay. So then the concept was to use straight shaft piers as settlement reducers, where the straight shaft piers would go down to a dense silt layer that was high capacity, but which you couldn't bell on. So you couldn't put a bell on it to take the full capacity, but you could put these settlement reducers, I call them, because then the stress level in the soil in the shaft, you don't have to meet the same factor of safety criteria and so forth, because they're not required structurally. They're just intended to reduce the settlement. you meet your structural requirements by the design of your mat, or in this case we used large strip footings sitting on the dense upper sand layer. And this is a picture of it basically. You have a strip footing here, or it could be a mat, sitting on in the dense sand, or medium dense sand actually, over a thin stiff clay crust, then followed by the soft clay, and then you've got a thin stiff clay, and then dense to very dense water-bearing silt down here. If you just use the strip footing here and using this sand layer as sort of a mat, is the reason why you can get by with a strip footing rather than a mat here. The predicted settlements, because of the consolidation of the soft clay, is on the order of 8 inches. And this, of course, was totally unacceptable. So the logical thing would have been to put it on deep foundations, which is what the original geotechnical engineer did. But to see, but looking at it from using this straight shaft, which is fairly cheap, you just you drill a straight shaft down to this very dense water-bearing silt. It's open, and you put the concrete in before you have a problem with this water-bearing silt. It's dense, but if you took the time to bell on here so that you didn't need this mat concept, if you took the time to bell down here, you'd have a blow-in. So you couldn't do that, but you could do this open shaft. We did some calculations that indicated we'd initially, when you put the load on here, when you built the building, a lot of the load, more like 60% or more of the load would go into the mat, and 40% into the shaft. But then as consolidation occurred in here, more of the load would go into the shaft, and you'd eventually end up with reversing, having at least 60% of the load being carried in the shaft and only 40% being carried, 40% or less being carried up here in the strip footing. But we wanted to instrument it to see if it actually would work this way. I mean, this system, the city structural engineer designed it so that with a lot of, if we were off, plus or minus 50%, he was covered in his design of his footings, and it was eventually the city eventually bought it. But we wanted to instrument it to see how it actually behaved, how close we were, and of course, in these situations, people don't like to spend a lot of money, so we didn't get as much instrumentation as we would like. But we did get some instrumentation on a couple of columns and also in the shaft. There's a lot more details in the paper. I should say something about how we looked at the settlement reducers. Normally, settlement reducers are used in friction pile design, where you want to reduce the predicted settlement, where you've got a mat on piles over extensive clay deposits, and you without the settlement reducers, the mat would be settled a lot more than it does with if it's on piles. But this is one of the few times I've seen it used where the piles go down to a dense, the settlement reducers, I want to call them, go down to a dense layer. And in that case, you want to be careful. We felt okay using it here because we were sitting on a granular layer, and the failure point, if you have a failure point that's different from what you are planning, you're okay, because all that happens is you keep pushing into the ground. Your settlement reducer keeps pushing into the ground and taking more and more load. However, if you've got a hard cohesive or brittle bearing deposit, it might not work so well. If you're wrong about where this occurs, you don't want to go past this, because then all of a sudden it doesn't carry the load it's supposed to, and you could have undesirable consequences. So in this case, again, it worked out quite well. This is a table that shows the actual load, calculated load from the instrumentation and the calculated the calculated load in the column, and then the calculated load in the shaft, and of course then you can calculate the bearing pressure, and you can see very high. The shaft here, and the one interesting thing that isn't immediately obvious is that we instrumented, one of the columns that we instrumented was at the end of the strip footing, and another was an interior column. And the end of the strip footing, the column carried a much higher percentage of the load than the interior column carried. And that's because it is at the end and it doesn't get the benefit of the strip footing effect on the other side. So at the end of the strip footing, where this column is, a much higher percentage of the load goes into the column. And of course, this is a factor. This is a very high bearing pressure, and is probably close to the failure point on that dense silt. But even if you exceeded it isn't going to be a brittle failure. It's just going to push further in. And the measured settlement was only 1.25 inches rather than the 8 inches. And on the interior column, the settlement was even less. The bearing pressure is less, so there's a higher percentage of the load being carried in the footing. There'll be some additional settlement over time. However, at this point, this is actually 4 years after construction, so there isn't an awful lot of settlement. So, and in actual fact, we had predicted that using the pressure meter data. We made one assumption. To be a little on the conservative side, we assumed that because that dense silt was saturated, there would be some loosening effect, though it would tighten up when the concrete got in, it wouldn't tighten up to where it was before. So we cut the pressure meter values in half, basically, and where we had originally predicted the 2 inches of settlement, looks like we only got about half what we predicted. So we probably would have been better off matching data if we hadn't made the reduction in the pressure meter data. But conceptually, I think this worked very well. The client was very happy. And a conclusion from this job: innovative, cost-effective solutions to foundation design problems are sometimes possible using combinations or mixtures of foundation elements, provided that ground deformation and response to structural loading can be reasonably predicted within allowable tolerances. This is another case history where we were able to do something innovative by using the pressure meter data to predict how the building was going to perform under load. And this tells the concept, but before I talk about that, I should say more about this particular project. There was a building there already on belled caissons. It was an 11-story building, an old building on hand-dug belled caissons, and there was a raft of them, and it was a deep 3-level basement. And so they wanted to build a 35-story. They wanted to take down the existing structure and build a 35-story new structure. And with all those belled caissons in the way, it would have required, moving around and putting the new structure on rock caissons. Again, rock caissons being very expensive, they were asking, well, what else can we do? So the concept here is to use the deep basement excavation stress relief in combination with a new basement mat over the existing foundations to maximize the number of additional floors possible at the site. And we didn't know in advance whether how many floors we could get. So the developer was a little bit open-ended, to try to save money, not to avoid going to rock caissons. He was open-ended on, it could only be 33, okay, but he wanted 35 stories if he could get it. So that's the concept. You take advantage of the stress release from the basement excavation. You've got you put a mat in at bottom basement level, and you spread the load around on the existing caissons. Of course, those existing caissons then have to be. Here's a picture. Here's the existing caissons. Here's the bottom of the mat, medium to soft clay, and the existing caissons are on a very stiff to hard silty clay. Not good hard pan, not our good Chicago hard pan, but I think the bearing pressure for those the existing caissons calculated out to be something like 16 KSF, which is higher, by the way, which is higher than the 12 KSF, which was the code allowable in those days. But anyway, that's what it calculated out, the 16 KSF. So this is a picture of the soil profile. You can see the soft clay here, the high water content, lower water content down in the very stiff clay where the existing belt caissons are, lower strength in the stiff clay below the mat, then increasing strength in the hard clay below. So on the geotechnical analysis, well, I sort of explained this. Maximum building height, number of floors at site with existing belt caissons, foundation system left in place to carry its share of the load. Take advantage of the pre-stress effect. Using the pressure meter data, calculate the maximum sustained load that can be carried by existing caissons without exceeding the creep pressure. Calculate the settlement under that load. Calculate the pressure that the mat can take for equivalent settlement. Combined loads at equal settlement represents maximum sustained building load that can be applied. That was the approach. And the structural engineer stiffened up the building. He was able to put in some sort of shear walls in the basement to help stiffen up the building. He wanted to use a rather flexible mat, so the mat was only like 3.5 foot thick over the existing caissons, and because he wanted to save as much space in the basement as he could. He did a three-dimensional SAP analysis to determine the overall behavior using the Geotechnical developed springs. We gave him the springs to use based on our pressure meter analysis and calculations. And this is the structure. Nobody wanted to pay for settlement measurements. We tried to get the contractor to pay. We tried to get the owner to pay. But nobody wants settlement measurements up front. The actual settlement was a little less than the predicted settlement, but not bad. In other words, the predictions were not bad, and they were on the conservative side. So we were happy, the client was happy, everybody was happy. Okay, moving on to the fourth, I think this is the fourth case history. There are 5. The Petronas Towers. When we worked on these towers, they were going to be the world's tallest towers, and they were the world's tallest for a while. The 1,482 feet tall, they're no longer the world's tallest. However, as far as I know, they have the world's deepest high-rise foundations. The foundations go up to 430 feet, and the world's deepest ground improvement, up to 530 feet. And this is a picture of the Petronas Towers, and the geology is terrible for trying to build the world's tallest buildings, particularly when you're going to try to connect them with a bridge. But this is a limestone valley here. This is over 200 meters. Never found the limestone in the middle here. It's 200 meters deep, but it's karstic limestone with cavities and fissures and voids, and there are some huge caves, not right here, but elsewhere, not too far. There are some caves in the limestone that you can go visit. So it's karstic limestone, so it's a terrible place to build this. This Kenny Hill Formation is weathered residual siltstone, sandstone, shale type of thing, very dense, but it's weathered down to soil. And the concept is, well, first I should say, the owner wanted zero differential settlement. Well, the design team said that's impossible. We can't build this with zero differential settlement. So it was agreed after some discussion and analysis that we should set a goal of a half-inch differential settlement from one side of the mat to the other, and that the design solution was a mat on friction piles. And the way we would control the differential settlement was by varying the length of these friction piles. And they vary from maybe 40 meters to 130 meters in length. And they turned out not to be piles at all, but barrettes, because the contractor building the slurry wall around the site, of course, he has that gives him a Barrette drilling machine right there. And he won, it was bid both ways, Barrettes or piles, and the people bidding Barrettes won. So these are actually Barrettes rather than piles. In predicting the settlement, the predicted settlement would be based on modulus values, based on board pile load testing. There were 2 load tests performed, and extensive in-situ pressuremeter testing. And then we thought we would use a simple equivalent footing approach to calculate or predict the settlement, and the structural engineer was going to use a more sophisticated finite element approach. And then we would monitor the settlement and see how it actually turned out. Just to give you an idea of why this Kenny Hill Formation is very dense. The average blow count in here is over 100 blows, so it's very dense soil. It's probably better than our dense hardpan even, very dense. You can see the very dense 100 blow material, or better. Although there's occasional little thin weathered soft seams in it, but and also some very dense hard seams, 300 blow material. So the range from 30 to 300 with the average over 100, I would say, is a fair depiction. And the pressuremeter test results, I think there was, I forget how many pressuremeter tests, I think there were a couple hundred pressuremeter tests, a large number of pressuremeter tests. And the average values for the initial load, you can see the range, initial load range from a low of around maybe a little under 40 MPa to a high, let's see what's the high here, almost 150 MPa. Then on the unload rebound modulus, and here the unload or rebound modulus were fairly close to the same, so it didn't make much difference which we used. But the range of pressuremeter values, low of, what's that, maybe 176 MPa and a high of 535. But the average rebound modulus was 267 MPa. The elastic modulus back calculated from the caisson load tests was around 200, it was over 200. And allowing for the fact that the caisson load tests were performed in an area that was thought to be a little bit poorer than here, the value of 250 MPa was selected for the modulus to use in the design and the calculations. And the simple equivalent of footing method, you know, we just took a initial. This was before the variable pile lengths. I think we were working with 60-meter piles here, which is probably not the average between 40 and 130, but it was the starting point for what we were using. We used 60-meter piles of equivalent footing, then at about 40 meters, and then calculated and using a slope of 1 to 4. below the load spread from the in friction around the block. In the equivalent footing method, of course, you assume a block analysis. You assume all of the piles in the soil in between act as a block, and that you can replace that block with a footing down at about 2/3 depth, assuming that the friction spreads out on some slope. We conservatively took a 1-to-4 slope, and then you assume that larger footing down at that level, and then you predict the settlement that will occur below that level, and then of course you have to add to that settlement the compression in that upper zone that you've in that equivalent footing depth. You have to add the elastic compression in that zone. And this won't go through the time to go through the calculations, but the calculations are in the paper, and they're fairly straightforward for the equivalent footing method, both using the Menard approach and also using the elastic theory approach, which we mentioned as the two methods that we use for predicting settlement. And just as an example, using the Menard approach, the settlement predicted settlement was about 41 millimeters, and that includes 27 millimeters of soil compression below the equivalent footing and 14 millimeters of elastic compression above the equivalent footing. By elastic theory, it turns out to be 59 millimeters below the equivalent footing plus 14 millimeters, gets you up to about 73 millimeters. So the elastic theory gives higher values than the Menard theory. And I think if you doubled, we actually used this data on another job, similar job, where we decided we would double the modulus, because here, if we doubled the modulus using this equivalent footing approach, we'd get a settlement that would just about match the Menard settlement. And you'll see what happens and how it actually came out. These were the predicted settlements using the SAP, the computer model, which was an elastic model. And again, 73 millimeters maximum kind of matches our simple hand calculation with the equivalent footing approach. And again, these are the two towers. They both are predicted to settle about the same. And the differential settlement across the tower was kept, this is predicted now, was kept to less than a half an inch. The maximum goes from across here, what's that, 68 to 57, about 11 millimeters, so slightly less than half an inch. So in theory, we achieved our half-inch goal. Now, what happened? This is the actual settlement. And when it was topped out, it hadn't even reached 30 millimeters. Ultimately, the last readings we got with it occupied up to level 55, maximum settlement was about 30, average settlement, that's the range of settlement, the maximum average settlement, about 35 millimeters. So it's still less than even the amount of settlement that we predicted using the Menard approach, and it's only half, or it's less than half the settlement that predicted using the elastic approach with the elastic modulus taken as the rebound modulus on the pressure meter test. Now, one of the things that's interesting, you look at it and you say, well, what can we think about to make this closer? You always like to be a little bit closer. So if you look up here, the board piles were put in from a 4-meter depth level, and the basement with the mat and everything took them down to about 24 meters or something. So there's a 20-meter excavation that occurs after the board piles are installed. So I think there was a pre-stressing effect. If you put the board piles in before you do the excavating, there's a pre-stressing effect. And so until you get that amount of load on, you're going to have a very flat slope of your settlement curve. And I think that's represented there. It's a flat slope. We're just starting to overcome the pre-stressing effect from the basement excavation. And then we, of course, then a steep slope as we're loading, and then, of course, a slight slope as we're doing the live load addition. If we took into account that pre-stressing effect in our settlement predictions, we'd knock off maybe 20% of the prediction. So instead of, we'd be a lot closer. If we knocked off 15 or so millimeters, we'd be much closer to the actual prediction. Or not 15 millimeters, but about 1/4 of the predicted of what we predicted. So that with the Menard, where we predicted like 41 millimeters, if we knocked off 1/4, we'd be pretty right down in there in that 30 millimeter range. And the elastic theory approach would be closer too. What did we learn? In-situ testing with empirical correlations works well enough for engineering purposes. The Menard empirical procedures yield better settlement predictions compared to elastic theory using test pressure meter modulus values as the Young's modulus for the soil and geologic conditions reported herein. This is just this job. Simple hand calculations for settlement and bearing capacity can be as reliable as sophisticated computer solutions. And innovative, cost-effective foundation solutions are often possible with close interaction of geotechnical and structural engineer and cooperation of experienced contractor. And the final case history is another one of these interesting ones with a lot of existing foundations. This is, for those of you who ever come to Chicago, this is 111 South Wacker Drive. I think it's a 52-story office building, new one. And it's built where there was like a 20-story office building that we did the geotech for. So they take down, to me it was nice looking. It was the old USG building. And it was nice looking and everything, but that's progress. They took that down and wanted to build a taller one. Unfortunately, all the existing hard pan caissons were there in the way. And the existing caissons are the dark ones, and the new ones are these. Now, you're putting in new ones where there are existing ones. How can you do that? Well, the only way you could do that is if the new ones would go in below the old ones. Then, as long as you got your shaft down by the old bells, you could then bell deeper underneath the existing ones, and then put a mat over the whole thing, and get the advantage of whatever capacity you have in the old, plus whatever capacity you get in the new, and get all of this to kind of work together, and see what you get that way. And so that was the design concept, and our job was to do enough pressure meter testing and to help calculate what the anticipated settlement would be with this type of design. This shows the building site with a couple of cross section where all the borings were. We had 3 sets of borings from the original borings, and then a couple of sets more recent borings. And the actual profile, stiff clay, and then you could see where the existing caissons were supported near the upper part of the hard clay. Down below, you've got water-bearing silt problems over limestone bedrock, or dolomite bedrock rather. Okay, yeah, this shows some of the existing and the new caissons, similar, just another cross section. And this shows a plot of the data. It's probably easier for you to look in the paper than to look up here, but it shows all of the pressure meter data and how we picked our design values. everything went smoothly. I think we predicted something on the order of an inch settlement. An inch seems to be a magic number. But there was a lot more that had to be done before this project went forward. There was a lot of investigation of the existing caissons, coring of the existing caissons to prove that they were good, even though we had done all the inspection ourselves and we were confident in the quality of the caissons. We had to do enough verification testing to satisfy everybody that the existing caissons were good. And one of the problems that occurred was on the perimeter of the job where the existing caissons got too close. I mean, where the new caissons, there weren't existing caissons on our property at that location, but the new caissons got too close to some rock caissons, adjacent rock caissons, and they had to blow in the bell while constructing the bell from the adjacent rock caissons off-site. In other words, the next building to the south. And so one of those caissons, there was efforts made to save it, but in the end it couldn't be saved, and they had to put one caisson down to rock. The other caisson was almost good enough. If it could be supplemented with micropiles, we could get the capacity we wanted. So we put a collar of micropiles around the caisson to get the capacity that we needed, and then the project went forward and they built it. And this is, and then of course they did monitor the settlements. They did get settlement data, and the settlement. Let's see. I guess the predicted settlement using elastic theory in the core was about 1 inch. And I think you can read in the paper what the actual settlement was. I don't think we were able to take a settlement measurement on the core, but let's see, using the Menard's method, the predicted settlement was a 1/2 inch, and well, maybe that, yeah, the measured settlement was a 1/2 inch. I don't know if you can read that yellow. I'm kind of colorblind, but I think that yellow was a 1/2 inch. And then the other predictions are here. These are the predictions, and these are the actual measured amounts, and they're fairly close. I think we got a remarkably good correlation between prediction and performance, considering the fact that we had belt caissons at different levels on different materials, and we had the rock caisson, and we had an enhanced belt caisson with micropiles. So this summarizes more or less what I just said, and I think with that I'm open to questions, and I think I got a minute left. I was going to say that in our experience, there have been cases where using our procedures, the way we use the Menard rules and everything, doesn't give a good correlation. And one of those locations is where you've got a lot of layered soils, and for one thing, it's difficult to get representative data anyway in layered soils. You have membranes blowing if you have a hard layer and a soft layer and so forth, so it's very difficult. But even if you could get it, sometimes those hard layers mask transfer load in such a way that it's almost as if the soft layers weren't there. In fact, we've been on jobs where those soft layers are actually under-consolidated because of the masking effect of the hard layers. And that's one formation. And another is where you have weakly cemented sands, like a very weak sandstone, and where you may be using high enough bearing pressures to collapse the cementation, and where sometimes you get an alpha in the Menard approach, you know, the initial modulus to the reload modulus, the factor will be a factor of 10. Or the reverse, I guess, would be a factor of 10. The reload modulus is 10 times as stiff as the initial modulus. So there's been a lot of stiffening occur. So those are two situations where using our procedures, we haven't gotten good results. But with that sort of commentary, I'll again open it up to questions.
Any questions? Yes, sir. Yes.
Clyde, in the last project, did you look at micropiles as alternative to your caissons?
No, we just used the micropiles on the caisson that couldn't go in as designed because of the water problems, and we couldn't complete the bell. And so it was an enhancement operation to enhance the capacity. We didn't look at micropiles for the whole design because it's too costly. I mean, the micropiles, they're good for certain things, but they seldom work out to be a total design unless there's something, unusual. But at least that's our experience. Yes?
I'm interested in your application of sediment reducers as
Yes.
well. And you talked about not wanting to go beyond the capacity. And what sort of percentage capacity of the pile, or would you feel comfortable working with this sediment reducer?
Well, in theory, you want to. What we've said and what we've done here is you don't want to go beyond 50% of the structural capacity, so that you could be, and that's assuming you're not going to be off by more than, you wouldn't be off by more than 100%. You don't want to fail the structural element. So you would go up to 50% of the structural strength. So here, like 76 KSF was the bearing pressure on that element. It's like 35 tons per square foot. That's like 600 PSI, 500 PSI. So it's not a very high stress as far as the structural element is concerned. Now, as far as the bearing capacity is concerned, what you're thinking is it doesn't matter if it fails, as long as it's not a brittle failure. It's just going to push a little bit further into the ground and to develop its capacity. I mean, that's the concept. And if you're using it in a bearing capacity way like this, normally it's just used in friction soils. So that was the unique. We've done this twice on two different projects, both of them where the end bearing was in a granular material. So we didn't feel we had to be concerned with a brittle failure, and they both worked well.
I have a question. A number of people thinking about settlement would use the consolidation test. How do you feel about consolidation test, maybe not versus pressure meter, or you seem to have elected to go with the pressure meter?
In pre-consolidated soils. Because those of us who have done a lot of consolidation tests know how questionable our pre-consolidation pressure pick is from a consolidation test, unless it's a very good one. We have different construction methods to get the pre-consolidation pressure, and unless you have a good undisturbed sample, you have quite a range in what you can get out of the pre-consolidation pressure. So, and if you're going to have that kind of variability in selecting your pre-consolidation pressure from a consolidation test, and you can get close with the pressure meter creep pressure, and it's so quick, why not use that? So that's what we do. Now, it doesn't, of course, in soft clays, when you're going to have consolidation, like on that Southside project, we ran consolidation tests on the soft clay, because there is some pre-consolidation in the soft clay from past desiccation and things like that. And when you get into soft clay, the pressure meter doesn't give you you can't get it in soft clay. But so we run the consolidation tests, get the pre-consolidation pressure, and also so that we can make our calculations for settlement. that project was just barely doable the way we do it. I mean, the rules we like to have is it's got to have a factor of safety of 2 geotechnically without the settlement reducers. So the mat, the footings on the dense sand and this forming kind of a mat over the soft clay, you had to have a factor of safety of 2 against ultimate bearing capacity failure. So that's one rule we would keep. And then the other is have a factor of safety of 2 on the structural elements. So if you're off by a factor of 2 or a factor of almost 2, you don't fail the structural element. And then the other is that the structural engineer has to do a sort of a parametric analysis on the reinforcing required in the mat or the footing, depending on how much he wants to believe you on what load's going to be carried by the shaft and what load's going to be carried by the footing in this case. So he has to do a kind of a parametric analysis and then decide how conservative he wants to be in reinforcing the footing. So that's why it's a good interactive approach.
What about time dependency? You know, you showed us some settlement and you give only one number. I kind of wondered, is it after 2 months?
Yeah.
Is it after 2 years?
Yeah, well, there is, of course, time dependency. And the pre-consolidated situations, we just, we say, doesn't matter, it's not going to be much, okay? Now, that's probably not correct. It's going to be something, but it's not going to be enough to cause anybody heartburn. I mean, that's the assumption, and we haven't had any problems. Nobody's gone back and tried to measure it several years later. Because it takes a couple of years to build these things. So in a pre-consolidated soil, a couple of years is a fair length of time. So we haven't done that. The chances are the settlement would be greater. Like if you went back and, I really don't think it would be much greater in a deposit like Petronas Towers, that very dense material. But in hard clay, yes, I think it could be greater. In this Southside project, where there is consolidation going on in the soft clay, there's this transfer of load from the footing to the pile as the soft clay consolidates under the stress imposed by the footing. That takes time, and that probably was 4 years, but 4 years probably isn't enough. But that's a significant length of time for our soft clay, so you probably got 80% of it, in 4 years. And then there's going to be a gradually more, if you come back and check it in 10 years, something like that.
Thank you.
Thank you, Phil.
Jean-Louis asked me to try to tell you some stories about things that would involve my dad and Spin and I. Spin not being a geotechnical engineer, the only story I thought that might be interesting for the group would be for him to tell you about our experience buying a T-model in Austin and driving it home to the dismay of my dad. We were on a Boy Scout trip, and the trip originated in Austin. We were members of an Indian dance team. We went up into Indiana, and some older boys needed some money. We loaned it a little bit to them, and then they got to St. Louis, and they wanted to borrow some more money. We loaned it to them, started buying bread, peanut butter, and jelly to get home. We made it, but we had so much money invested in them that we wanted collateral, and they put up a T-model Ford. So when we got to Austin, for another $10, we got the Ford. We were supposed to be home at 4 on the bus from Austin. My dad met the bus. The next bus was 6:30. My dad met the bus. This went on till 11. And we got on the road about 7, we made it to Elgin, and we stopped and let the Model T cool down, put some water in it. We came on to Caldwell, stopped, let it cool down, put some water in it. Started to Bryan, and the lights started getting dim, so we reached in there and unwired the lights, and when we saw a car coming, we'd wire up the headlights. Or approaching from the rear, we'd wire up the tail. We made it to the courthouse in Bryan, and there used to be a Gulf station there, so we got a 50-cent charge on the battery to get home. We made it home about 1 o'clock, rang the doorbell. My mother answered it. Well, boys, how did you get Mother come out and see our new car? Whee! You boys will take that down, bring back tomorrow. Well, Mother fed him a real good breakfast, and we worked on him. He didn't stand a chance. We convinced him that, Daddy, we can't do it tomorrow, but we can do it this coming weekend. We'll do it this weekend. Don't you worry, Daddy. And we got him to the next weekend. He was Friday in Bryan at the barbershop getting his shoes shined, and he started telling the shoe shine man about how he knew exactly where his 2 boys were. After school, they were home working on that Model T. So we kept it for a year. And I got tired of it one day. I went coon hunting, and it wouldn't come up the hill because I'd let the oil and water get low on it. So I ran off on the side of the road, walked home. Philip said, "Where's the car?" I said, "Down on Highway 6. You want to buy my hat?" I sold that. But one thing I have noticed with these 2 pictures over here is my father, the one on my left, I guess that would be your left. I really find it interesting in that he is sitting there listening, and you better be careful because he's going to tell you in just a minute how it is. And then the other man is Dr. Tazagi that my father studied under. Now, I personally never knew Dr. Tazagi, but he knew me. And he used to talk to me, and I was about that long. I want to thank you for the privilege of being with you all, you gentlemen. It's indeed an honor for Philip and I. It's frankly rather humbling on my part, but made very proud to have had my father, to have known him, and to have had the privilege of growing up under his leadership. Thank you.
Well, thank you very much for the privilege of being here. Thank you. Thank you.
Thank you.
This is the honorarium, and this is the plaque for the 14th Buchanan Lecture, In-Situ Testing, Soil Structure Interaction, and Cost-Effective Foundation Design. Thank you very much.
Well, thank you very much. Yeah.